Welcome back, students. Continuing from the previous lesson, to understand how nerves control skeletal muscle movement, it's not enough to know how action potentials are transmitted between nerves and muscle cells. We also need to understand how skeletal muscle contracts. Think of everyday objects that contract. Rubber bands, elastic straps, or springs. How do they shorten? Are our muscles similar? Let's examine them under a microscope. Take the biceps brachii as an example. When you flex your elbow, your biceps bulges. The bulging middle portion is the muscle belly, with tendons at both ends attaching the muscle to bone. This is the macroscopic view of muscle. Microscopic observation shows skeletal muscle cells are fibrous, thus called muscle fibers, and muscle fibers are the basic structural and functional units. Adult muscle fibers are about 60 micrometers in diameter and can range from millimeters to tens of centimeters in length. Each fiber contains hundreds to thousands of myofibrils arranged in parallel. Myofibrils are about 1 to 2 micrometers in diameter and run the full length of the cell. Distinguish muscle fibers from myofibrils. A muscle fiber contains many myofibrils and a developed tubule system. In short, myofibrils plus tubule system equals muscle fiber. Under the microscope, myofibrils show regular alternating dark and light bands. Hence, skeletal muscle is also called striated muscle. The dark band centers on the M line, and the H zone flanks the M line. The light band centers on the Z line, and the region between two Z lines is a sarcomere. Thick filaments anchored at the M line form the dark band. Thin filaments anchored at the Z line form the light band. In the sarcomere, the H zone contains only thick filaments. The I band contains thin filaments, with overlap elsewhere. Thick filaments are composed of myosin. Many myosin molecules packed together by their tail regions, with their heads projecting outward to form cross bridges. Each thick filament has roughly 300 to 400 cross bridges, which have ADPase activity to hydrolyze ADP for movement. Thin filaments consist mainly of 3 proteins: actin, tropomyosin, and troponin. Actin molecules polymerize into a double helical backbone, with tropomyosin molecules forming strands that wind along the grooves, and troponin anchors tropomyosin to actin. Next is the tubular system, which are membranous sacs and tubules surrounding myofibrils. Mainly the transverse tubules, T-tubules, and the sarcoplasmic reticulum. T-tubules are invaginations of the sarcolemma into the fiber and transmit excitation rapidly into the cell interior. The longitudinal tubules are the sarcoplasmic reticulum, running parallel to the fiber axis, forming terminal cisternae near T-tubules that store large Ca2+ reserves. Ca2+ concentration in the terminal cisternae is roughly 10,000 times that of the cytosol, with L-type Ca2+ channels and Ca2+ pumps embedded in the membrane. The sarcoplasmic reticulum stores and regulates cytosolic Ca2+. Having covered structure, how does muscle contract? Imagine interleaved playing cards when shuffling, which resembles the interleaving of thick and thin filaments. Overlapped regions are thicker, non-overlapped regions are thinner, and muscles bulge when contracting and thin when relaxed. In 1954, Huxley and colleagues discovered that the length of the A band does not change during shortening. While the I band and H zone narrow, the opposite occurs during stretch. They also found filament lengths remain constant, but the degree of overlap between thick and thin filaments changes. Based on these findings, Huxley proposed the sliding filament theory, which explains the mechanism of skeletal muscle contraction. At the molecular level, how does sliding occur? When the muscle is relaxed, troponin and tropomyosin block myosin binding sites on actin, preventing cross-bridge binding to actin. When Ca2+ binds to troponin, troponin changes conformation and moves tropomyosin away, exposing the myosin binding sites on actin, allowing myosin cross-bridges to bind and produce sliding contraction. Thus, Ca2+ plays a key role in the contraction-relaxation cycle. So how does an action potential trigger intracellular Ca2+ changes? Physiologists call the mechanism coupling electrical excitation to mechanical contraction. The excitation-contraction coupling. Excitation-contraction coupling occurs in the triad structure and involves three main steps. 1. Conduction of excitation. The action potential travels via the T-tubules into the triad, penetrating deep into the muscle cell interior. 2. Ca2+ release. The potential on T-tubules activates numerous Ca2+ channels in adjacent terminal cisternae and SR membranes, causing Ca2+ to flow into the cytosol down its concentration gradient, bind to troponin and induce sliding of the filaments. 3. Ca2+ reuptake. Ca2+ pumps on the SR returns cytosolic Ca2+ into the SR against the gradient, lowering cytosolic Ca2+, allowing troponin to release Ca2+ and the muscle to relax.